Cheers, my cool calculus comrades. I'm Calculus Christian, and today we're going to be talking about some logarithmic differentiation. So, you want to use logarithmic differentiation whenever you're taking the derivative of a variable to a variable. You see what I'm saying? So, for example, x to the x power, maybe you got x squared plus x, all that to the x power. So, taking the derivative of stuff like that. So, for example, if we want to take the derivative of y equals ln of x to the x power, our first step in this derivative would be putting a logarithm on either side. So, ln of y equals the ln of x to the x power. And then we would want to bring this x down. This x got to go down over there. So ln of y equals x to the ln of x. Okay, now we're going to take the derivative. So the derivative of ln of y is 1 over y times the derivative of y, which is dy dx. And then equals, we got to do the product rules here. So derivative of x is 1 times ln of x plus x times the derivative of ln of x, which is 1 over ln x times the derivative of ln of x, which is 1 over x. And the x's cancel. So let's just simplify this a little bit. 1 over y times dy dx equals ln of x plus 1 over the ln of x. So now we need to bring over the y, so the dy dx can be isolated. So when we multiply y, we want our answer in x's, and we can actually, when we multiply the y, we can substitute ln of x to the x power for y. So we're multiplying the y over, and then it's ln of x to the x power is y times ln of x plus 1 over ln of x. So that right there is your derivative equation. It's a pretty big one. Okay, so you can also use logarithmic differentiation for when you're doing derivatives just to speed it up. So you could do logarithmic differentiation when you got a big problem, like x squared plus 1 squared times x plus 1 over, let's just say 4x plus 3. So you can use the logarithmic differentiation here because you don't like taking the quotient rule and then doing the product rule inside the quotient rule is kind of tough. So just use the logarithmic differentiation here. So ln of y equals ln of this big equation here, x squared plus 1 squared times x plus 1 parentheses and then 4x plus 3. So now we can separate this log right here, so it'll be easier to take the derivative. So this is the same as ln of x squared plus 1. And instead of putting the 2 right here, I can bring the 2 down. And then we can add natural log of x plus 1. And then subtract, because the 4x plus 3 right here is on the bottom. So subtract ln of 4x plus 3, just using your classic logarithmic properties right there. Now we can take the derivative. So 1 over y times dy dx, of course, derivative of ln of y. And then we can take the derivative of 2 ln x squared plus 1, which is 2 times 1 over the inside, x squared plus 1 times the derivative, plus ln of x plus 1 over that thing is x plus 1, and then minus 1 over 4x plus 3 times the derivative of 4x plus 3, because chain rule. Then we can simplify this bad boy out real quick. So we got 1 over y times dy dx equals, what is that, 4x over x squared plus 1 plus 1 over x plus 1 minus 4 over 4x plus 3. So we just simplify that out a bit, and now again we're going to have to multiply by this y here to isolate the dy dx, and we can substitute y with this giant equation, x squared plus 1 squared times x plus 1 over 4x plus 3. So we just substitute that in when we multiply it over. So we're bringing it over, x squared plus 1 squared times x plus 1 over 4x plus 3. And this is all y, this guy right here, y. And then we multiply it by the derivative we got up here, which is 4x over x squared plus 1 plus 1 over x plus 1 minus 4 over 4x plus 3. Alright, so this is your derivative equation right here. Derivative equation for your original. So you can use logarithmic differentiation when you're doing variable to variable, like you basically have to do it then, but it also can serve as a good speedway when you're doing giant polynomial thingies, because those are just annoying. So that's about it with the logarithmic differentiation. I'm Calculus Christian.